Thanks for inviting me. It's a pleasure to be here. This is my first time in Vienna. It's very lovely. And this is also my first time in a long time giving a talk that's not about EPR and Bell's theorem and such things, which I'm kind of excited about, but also having reservations about after some of the earlier talks this morning, just because I think there's a lot of interesting stuff to say about that hasn't really come out. So I thought I kind of snuck this first bit in over lunch just to try to put some context to some of the things that we heard about this morning. So it seems like a big, theme of the conference and something that everybody's very interested in is this question about whether the world is local or non-local. My perspective on that is that it was pretty clearly established by Bell, even as early as 1964, that the world is non-local. Well, of course, we had to wait for the experiments, but, well, you know that story. There was a remark this morning about whether quantum field theory is some kind of exception to this claim, and I don't think it is. I think quantum field theory is not a local theory in the sense in question. But really what I wanted to say something about is this sort of like, what's the meaning of locality? Because I think the concept of locality that everyone has had in mind so far is some notion of like dynamical locality, okay, like influences propagating faster than the speed of light. And to me, that's the thing that's pretty clearly established by Bell's theorem and the relevant experiments. I'm not really going to talk about that. I just thought I would lay my cards on the table. But what I want to say is that there's this other notion of locality that has really not received any attention at all, not been acknowledged to exist at all. And I kind of sketched up one of these like causal structure pictures, which we usually think of as being embedded in, as a space-time diagram. A lot of the things on this picture, like if as we heard this morning, we seem obliged to take the quantum state as somehow physically real, to me that raises a different kind of locality issue than what we've heard about so far. Like to the extent that that's true, then all of the elements in this causal structure graph, the setting on some apparatus, the outcomes, which is maybe the position of some needle and ink on paper that gets printed later, and then of course the state of the entangled particle pair, all of these things are somehow described by a quantum state, which is a very abstract and strange kind of thing. It's a vector in a Hilbert space, or maybe it's something like a field in some kind of configuration space. I simply don't know how to understand any of those things as descriptions of objects living in 3+1 space-time, the way that these kinds of pictures, I think, assume and imply. And so to me, there's another kind of concept of locality there that hasn't been acknowledged, which sometimes goes by the name of local versus non-local beables, okay? And so in a way, that's what I really want to talk about here. I'm going to start by just saying a few sort of introductory things about Bohmian mechanics, because I like that theory very much, and I think it provides a kind of context from which to discuss some of these issues. And I also think that a lot of people, even who know something about Bohmian mechanics, maybe don't think about it quite the right way. And so I'll spend something like half my time trying to clarify some issues about that. And then I'll sort of briefly try to get to this point where I think Bohmian mechanics gives us a kind of useful perspective from which to think about this question of this other sense of locality, the existence of local or non-local beables. So hopefully I'll manage to get to that. Okay, so Bohmian mechanics in a nutshell. The theory is very simple. It's beautifully simple. It starts with the wave function, which obeys Schrodinger's equation all of the time. There's no caveats or footnotes about how well actually it collapses in such and such a situation. It just obeys Schrodinger's equation all the time. And then in addition to that, there's particles, so literal point-like, classical-like particles with some definite time-dependent configuration that evolves according to some simple equation that I've written here. And that's it. Okay, that's the whole theory. Okay, literally that's the whole theory. There's no measurement axioms in addition to that. There's just nothing else. That's it. Okay? And I think a lot of people who dismiss Bohmian mechanics dismiss it for reasons that have to do with their not fully appreciating that that's it. Okay? So I tried to, this is so important to me that I tried to capture it in a, whoops, I think I pushed the wrong button there. I tried to capture it in a picture. So here's my feeble amateur artist attempt to capture the world according to the de Broglie-Bohm theory, Bohmian mechanics. So the bottom slide is meant to be like the physical world that we experience when we open our eyes and look out the window. There's stuff, right? There's a planet, and there's a tree with leaves, and there's a happy little butterfly and the sunshine up there. There's even an unambiguously alive cat. which is a kind of pleasant thing. And so the point is like, okay, yeah, that's what the world really looks like, and we can understand that as literally being made of these particles, okay, that are part of the ontology of Bohmian mechanics, and it sort of looks right, okay? If you just draw what the particle configuration looks like and think about how it evolves in time, you get something that makes sense and that's consistent with just everyday experience of the macroscopic world, okay? But then in addition to that, there's this other weird thing, which is supposed to be like a conductor of an orchestra, but shaped like a capital psi, because that's supposed to be the wave function. So there's this other weird thing, which is sort of behind the scenes, okay? Not part of the ordinary three-dimensional physical world that we see when we open our eyes, which is somehow sort of orchestrating or choreographing the motion of the particles, okay? That's how the theory works. And I keep pushing the wrong button. Okay, so just a couple remarks about that. So it's crucial, as I've stressed, that the wave function that appears in the definition of the theory is not sort of the wave function that you're accustomed to dealing with from textbook quantum mechanics, but is instead the wave function of the entire universe, something that you sort of deal with in discussions of cosmology maybe, but not when you're solving textbook problems in quantum mechanics. And so it's far from obvious how this relates to the textbook formalism of quantum mechanics, okay? But it does relate to it, and indeed it does explain it, and so I want to take a few minutes and try to explain that. And so the object in the theory that plays a crucial role in explaining the textbook quantum formalism is this thing called the conditional wave function, which I've written the definition for here. It's literally just, you take the universal wave function and you evaluate it at the actual sort of location of the Bohmian particles for all the particles that are outside of your subsystem of interest, okay? So that's what I've written there. It's easy enough to see that the guidance formula, like the second equation that I wrote on the earlier slide that says, what the velocity is of the particles, it's easy to see that you can reformulate that for each individual particle in terms of the so-called conditional wave function for that one individual particle. It's just sort of the same law re-expressed in terms of the conditional wave function. Okay, so this is just definitions, and the claim is that like this object, the conditional wave function of some subsystem, or as we'll sort of take it for the rest of the talk, like just some random one individual particle that we're interested in treating quantum mechanically, the claim is that that thing acts the way that the normal wave function of textbook quantum theory should act, according to the fundamental laws of Bohmian mechanics. So let me try to convince you that that's true. So there's sort of two cases. The first case is that the particle of interest and the rest of its environment are not interacting, okay? So take the situation where the potential separates like this and there's no entanglement. It's then sort of trivial fact that the solution to the Schrodinger equation for the wave function of the universe takes this separable form. And so then up to an overall constant factor, basically, then the conditional wave function of the subsystem is just the thing I called alpha here, the thing that you would ordinarily take as the wave function of the subsystem when it factorizes and therefore exists according to ordinary quantum mechanics. And it's also straightforward to show that as a consequence of the fundamentally posited Schrodinger equation for the universal wave function, the conditional wave function will just obey its own Schrodinger equation. Technically, there's this sort of extra time-dependent term in the potential, which has to do with the fact that the way I defined the conditional wave function, it's not normalized in the way that wave functions sometimes are taken to be. But that's a sort of irrelevant little detail. Okay, so that's case one. And then, of course, the more interesting case is case two, where there's strong interactions between the particle and its environment, as, for example, when a measurement happens. So I thought instead of saying a lot of abstract things about this, it would be nice to have a kind of like toy model example system to think about. So I made up this system. Let's just take a one-dimensional particle in a box, which then is going to interact with an energy measurement device. And let's just sort of schematically take a couple of atoms from the needle on the energy measurement device, and we'll sort of treat those quantum mechanically and put all the stuff that's in gray, which is sort of how exactly the interaction works. We'll just treat that schematically by sticking some appropriate interaction term in the Hamiltonian here. So that's the last term with lambda. So sort of technically, I told you what hx is. That's just the Hamiltonian for a one-dimensional non-relativistic particle in a box. Simple thing. Hy and hz are just free particle Hamiltonians, okay? So the Poynter particles we treat as just like living there, and then the interaction Hamiltonian basically makes the Poynter particles move at a rate that depends on the energy of the particle in the box. So it's a perfectly nice sort of schematic treatment of a measurement. By the way, a lot of people sort of think, well, Bohmian mechanics is all about particle positions, and so somehow it gives you the right answers for like position measurements, but nothing else. So I'm kind of deliberately doing something other than a position measurement here. So as an initial condition, I just take, I don't know, some random superposition of the first several states for the particle in the box and put in Gaussian wave function centered at 0 for the two particles in the pointer. This is nice because then you can write down the exact solution of the Schrodinger equation for the system, and it's just what you would expect. The terms for the atom particles in the pointer just move to the right at some speed that depends on the sort of which energy the particle in the box has. So I tried to draw something, sort of the configuration space visualization of the wave function. So you start out with this overlapping stuff, and then as the interaction proceeds, you get these nicely separated packets. Okay, so that's what the arrow is meant to be. And it's easy enough to pick some random initial conditions for the Bohmian particle and solve numerically and find out what you get. So I just showed one example of that here, where you can see the pointer positions, which is the vertical axis in the graph, ends up at like 5 or something, which corresponds to the n=2 state. Okay, so the atoms in the pointer have moved the amount that we would expect them to move if what we're going to say is the energy measurement had the result n=2. So that's what's going on here. Is that clear? Okay. So having an exact expression for how the wave function of the universe here depends on time, and having solved numerically for the Bohmian trajectories, it's easy enough to go in and construct the conditional wave functions. I thought it would be fun to just show you some movies of what these things look like. So on the left here is the conditional wave function for the particle in the box, the x degree of freedom. And on the right is the one for one of the pointer degrees of freedom. So raise your hand if you think you know what these are going to look like. Does anybody know what these are going to look like? Nobody claims to know. Okay, well, that's good then. I'm not wasting your time. Okay, so here's the conditional wave function, and in case it's not clear, like the sort of x and y axes here are just the real and imaginary parts, and then coming out is x. Okay, and then it'll be a movie showing it as a function of time. So the initial condition here that you can see is just some random superposition of, I think, the first 4 lowest lying energy eigenstates. It happens to look like that. And here's how it evolves in time. Looks like some crazy jump rope game or something. But after some kind of random meandering, what do you think happens? I guess I kind of set it up at the top, so maybe I spoiled the excitement. But so the conditional wave function for the particle in the box ends up sort of at the end of the interaction that we would refer to as a measurement, ends up in what hopefully you can recognize in this representation as the n=2 state, right? Okay? You see that? You know what you're looking at? What happens to the conditional wave function for the pointer particles during this same process? So here again, they're not normalized, so it sort of goes crazy vertically, and you can ignore that. The point is it's sort of shifting to the right, but it's kind of not sure what it wants to do. So it's a little indecisive for a while. And then eventually it settles down into something that you would recognize as, the wave function that I would expect if the outcome of that measurement were n=2. Okay? So you can see that happening here. Okay, and so interestingly, you can do the same thing by picking some other initial condition, and sometimes it comes out differently, right? So the randomness in the system here is from the randomness in the initial positions of the Bohmian particles of the 3 degrees of freedom here. So this is the same thing, but for some different initial condition for the Bohmian position of the particle in the box that happens to give a different outcome here, n=4. So I'll let you watch the movie. Notice, so I maybe should have said this before I clicked play, but it starts exactly the same. Right? So the conditional wave function for that particle starts exactly the same in both cases, and then it evolves in some kind of crazy nonlinear chaotic way, but it settles down then into the n=4 state in this case. So you can see that here. And for those same initial conditions, the conditional wave function for one of the pointer particles kind of moves faster and settles down faster. So partly just because nobody claimed they saw this coming, you should have seen this coming. It's kind of trivial in a way, right? So if you think about like in terms of this configuration space map of where the wave function is, like as the interaction happens, I mean, there's some definite location, some dot in there somewhere which represents the actual configuration, x, y, z of the Bohmian particles. And then the conditional wave function is just like cutting along some direction of that by evaluating it at that point, right? So when the dot is in sort of the second lump, you cut that across horizontally by just evaluating that wave function at whatever the actual values of y and z are inside of that thing, and you of course get the n=2 state or whatever. But my experience is that if you try to explain it like that, like everybody kind of nods, but then they don't really believe you. So I thought maybe it would be helpful to see a movie. Okay, summary so far. So the Bohmian conditional wave function not only evolves in accordance with Schrodinger's equation in the types of situations where that's what the textbook quantum wave function is supposed to do, but it also collapses, right? That's really what we just saw. It collapses in precisely the kinds of situations where textbook quantum mechanics says that wave functions are supposed to collapse. And sort of the cool and interesting and amazing thing about this is that it does both of these things sort of automatically in the right kinds of situations without some kind of hand-wavy division of the world into these two different kinds of processes like von Neumann talked about and all these different things, right? So there's sort of nothing like the inconsistencies and ambiguities in this theory that give rise to what we call the measurement problem in ordinary quantum mechanics. And yet we sort of derive or predict the behavior of the quantum mechanical wave function. Yeah, sure.
How strongly does this conclusion that it collapses as it should depends on the interaction term you have added, which is unbounded from below?
Yeah, I think it doesn't depend strongly on that. I mean, of course, the real situation is much more complicated in the sense that, in the real world, there aren't just like particles that are completely isolated from their environment and then...
There is a theorem that says if the Hamiltonian is bounded from below, the wave functions will be quasi-periodic. Only because you had a linear term in px and py multiplying hx, which makes the Hamiltonian unbounded from below, you can violate that theorem. And in nature, Hamiltonians are bounded from below. So I'm very curious to see whether you can produce the same picture with a bounded Hamiltonian.
Yeah, so I don't really have anything to say about that, but I strongly expect there not to be some kind of fundamental problem where it doesn't work anymore, but maybe we can think about that later and talk about it later. Okay, so this is sort of the end of the Bohmian propaganda part of my talk, but I mean, I think it's worth really stressing, to the extent that one of the big questions of this conference is like whether maybe ordinary quantum mechanics might be viewed as somehow emergent from some different underlying theory, then really Bohmian mechanics should be taken quite seriously, I think, as a strong candidate for what that theory might be. It's at least, it's a theory that exists. We can see what it says, and it seems to say the right things. It seems to predict all the right things. It seems to allow us, in particular, to derive the rules of ordinary textbook quantum mechanics, which is, I think, a big part of what one means by trying to understand quantum mechanics as emergent. Okay, good. So having done that, now I'm going to turn and start adopting a somewhat different point of view that I think a lot of my Bohmian colleagues would not like so much, actually. So to get into this, I want to start by telling you about the existence of a kind of uniquely Bohmian approach to treating things in a semi-classical way. And mostly I just want to do this to sort of set up for something. I'm not actually so interested in this, but here it is. So consider, again, some simple two-particle system with some interactions. So if maybe, say, one of the particles is really heavy and the other one is really light, we have some reason to think that maybe we should be able to treat one of them in some classical way, whereas we want to continue to treat the second one quantum mechanically. Here's sort of how you do that. You take... instead of dealing with a wave function for the y degree of freedom, you just have, capital Y, the classical position of that particle, which obeys some classical equation of motion, and then a Schrodinger equation, right, a quantum dynamical description of the other degree of freedom. And I'm realizing that there's a typo where this is there a pointer in this? So that was supposed to be one of these weird script X's. So the point is that the feedback from the X system into the Y system, the sort of normal quantum mechanical way of doing that is to have that feedback go by the mean value, if you like, the quantum mechanical mean value of that degree of freedom, whereas Bohmian mechanics provides a kind of like obvious and natural alternative way of doing that, which is to have the feedback to the Y system go from the Bohmian position, the actual Bohmian particle location. Okay, so there's some papers. Xavier, who joined us, has written some papers about this idea, and other people have as well. And I don't really want to talk about it too much, but there's some literature that you can look at if you're interested. Mostly I wanted to sort of mention this because I think it's interesting to see how the derivation of this Bohmian semiclassical approximation goes, because it's something that you can actually sort of derive in a formal way in the context of Bohmian mechanics. And so I've tried to sketch that here. So the Bohmian description of the two-particle system, we start with sort of the wave function of the universe obeying this universal Schrödinger equation. And then in Bohmian mechanics, we have the two guidance formulas for how the positions of the two particles, x and y, evolve in time. And if you take another time derivative of one of those, you get something. You get that law can be re-expressed in some kind of F equals ma type terms, where there's this famous quantum potential term there, the capital Q, in addition to the usual scalar potential. Okay, and so in the semiclassical approximation, we assume that Q is negligible, and we just throw that term away. And then similarly, the conditional wave function for particle 1, so I've written down here sort of the full equation that you get from the universal Schrödinger equation. If you say, well, here's the definition of the conditional wave function, what's its time derivative? So basically that's the right-hand side of the universal Schrödinger equation evaluated at the actual location of the other particle, and then there's another term. And in any case, you get all that. And then the point is that the sort of Bohmian semiclassical approximation you get by throwing away these last two terms, okay? And so there's a lot to say about, like, well, under what conditions would you expect this to be justified, et cetera. But that's formally how it goes. So then really what I kind of want to put out there as an idea, this is an idea that I've been sort of trying to think about in my free time for several years, and I don't have as much free time as I would like, so it remains a work in progress, but at least I gave this idea a name. So sort of to contrast it with the Bohmian semiclassical approximation, I thought it was sort of illuminating to think of this other approximation scheme that one might adopt as a double semiquantum approximation, where you do something like what you're doing in the semiclassical approximation, but you split the fully quantum mechanical system in half and then treat both halves quantum mechanically, but receiving a sort of like classical feedback, if you like, from the other system, as in the semiclassical approximation. And so again, formally the way this goes is you say, well, I've got the universal wave function that includes some interactions. If I write down the equations that are satisfied by the Bohmian conditional wave functions for the two systems, those are written here. And then I can throw away the same terms that I would have thrown away for each of those pieces, sort of were I taking it as the quantum half in a semiclassical approach. And then, of course, I also have the particle positions that are each guided by their usual formula in terms of the associated conditional wave function. So this is, again, some kind of approximation scheme, obviously. You're throwing stuff away, so you're not going to reproduce the exact quantum mechanical results. You would only expect it to do that in the case where there's no interaction and no initial entanglement, so that the sort of even according to ordinary quantum mechanics, you would expect it to be able to treat it as two sort of independent quantum mechanical systems. So in some sense, then, this approximation is, think of it as a small entanglement approximation, just in the sense that it's exactly right only in the limit of no entanglement. So again, I was trying to come up with a sort of simple toy model example just to illustrate this idea. So again, suppose you have two one-dimensional harmonic oscillator systems, but with some interaction term. This is nice because it's easy to figure out the exact solution. And so if you start the thing in a state where one of the two systems has sort of one quantum of energy and the other has none, then they trade it back and forth, and the system kind of oscillates back and forth between the state in which particle 1 is excited and particle 2 is in its ground state, and vice versa, and it just goes back and forth. It's like a simple quantum mechanics exercise. But this is a nice system because it's sort of easy to treat also with what I've described as the Bohmian double quantum approximation. Double semiquantum approximation. I forgot my own acronym. Okay, so I've shown some results of that here. So this is like the coefficient from the ground state and first excited state term for particle 1. The ones for particle 2 just sort of look exactly the same, but they're opposite. So in the red is sort of what you would say according to ordinary quantum mechanics is like the probability for this system to be in respectively the ground state and the first excited state, so it just oscillates back and forth. And you see sort of something qualitatively, vaguely similar to that in the blue, which are just results of sort of numerical results with the BDSQ. And so the idea is that somehow it's getting something kind of qualitatively right about the behavior, but it's sort of obviously not very good. The quantitative details aren't right, the period is too long, and if you look carefully, you can see that like the probability for the first particle to be in the ground state kind of never quite gets to 1 the way that it should, okay? So anyway, that's a thing that exists, and you can solve it, and it's kind of interesting that you do even as well as you might. Sorry about the joke here. But really, in a way, this sort of idea that I've had in my head for some years is to go then beyond this kind of simplest so-called Bohmian double semi-quantum approximation by figuring out a way to include the information that was left out by crossing out those couple of terms in the sort of Schrödinger type equations for the other particles. And at least formally, it's easy enough to do that, or it's at least easy to see one possible way of doing that. So I've tried to indicate that here. So remember that the terms that we left out, well, sorry, I should go back to here. The terms that we left out involve sort of higher derivatives with respect to the coordinate of the other particle on the wave function that are then evaluated at the actual location of the Bohmian particle for that other particle. That's sort of the nature of what we've left out. And I probably should have said this earlier, but it's like, it should be obvious that those terms are precisely the terms which make, these one particle Schrödinger type equations nonlinear and non-unitary, right? So those terms are the sources of, the collapse of the wave function that we saw earlier in the movie, for example, okay? So the idea is let's find a way to sort of incorporate that information back in some kind of hopefully somewhat controlled approximation scheme, and we should be able to move back closer to the exact quantum results. Okay, so we could just do that. We could just say, okay, let's introduce this new sort of field, okay, associated with particle 1, which we sort of think of as deriving from Bohmian mechanics in the way that I've indicated here. But in the context of this, we would just take this as some other field. Okay, it's not exactly like the pilot wave field for particle 1, but some sort of higher order thing, okay, which is also associated with it and influencing its motion. Those things, it's again easy to derive from, again, the wave, the Schrödinger equation obeyed by the wave function of the universe. It's easy to derive some dynamical equation that these guys should satisfy. Higher and higher order terms appear, and so in some approximation scheme, we would have to then neglect those. Or maybe there's some better way, as I'm starting to think, as I sort of play around with doing this numerically and get what I think it would be fair to confess is garbage. There's probably some better way to package up all the information that was sort of left out of this simplest approximation scheme. There's some reasons to think that this is not a good way to do it, but this remains a work in progress, so that's really all I'm going to say. But there must exist some kind of sensible converging expansion here, which like moves this interesting approximation scheme closer and closer back to the exact quantum results. Okay, so then let me just say very briefly, like, what is the point of doing this? Like, who cares? So some people, I think, are interested in this because it might prove useful as a novel and uniquely Bohmian approximate treatment of many body systems, which I think is eminently worthwhile. But for me, the real motivation here is sort of more metaphysical, and it's this weird guy that was in the picture at the beginning, that is to say the wave function of the universe. And as I did manage to squeeze in at the beginning, I just don't really understand what kind of thing the quantum state of the universe is supposed to be. It's just not a local beable, and so it's very, very strange. I liked Bohmian mechanics because it's sort of off stage, and there's this other, there are local beables that look like the way the world is supposed to look, but it still bothers me that this thing is there. And so I think this kind of line of reasoning that I was trying to outline, I think maybe gives us a promising avenue toward what I've called a theory of exclusively local beables. That is to say, something in which, a field on 3n dimensional configuration space or anything like that simply doesn't need to appear. So I stuck this into over lunch. So this morning, Matt explained his principle of explanatory conservatism, which I liked very much. If there is a natural explanation for a quantum phenomenon, then we should adopt an interpretation that incorporates it. So I'm sure he wouldn't agree with this application of the principle, but to me, like, one of the most natural things in the world is explaining the results of the double slit experiment in a kind of standard Bohmian way. Like, Bell said this very well, like, is it not clear from the smallness of the scintillations on the screen that we have to do with a particle? And then is it not clear from the pattern that those make over time that there's some wave guiding the particles? So to me, that's very compelling. It's a very natural explanation of that phenomenon. And you see, that's sort of exactly where I want to go here, is like quantum mechanics, a reformulation of quantum mechanics in purely three-dimensional space, or 3+1 space-time, where we have particles and then sort of associated fields guiding them individually. And I'll just leave you with this last picture, which appeared in a philosophy paper. This is sort of supposed to be David Albert's understanding of Bohmian mechanics on the left and mine on the right, which captures it, I think, very nicely. So thank you.
Thank you very much.